Boom! Yes, folks, Hume again. How are you going? So in this video, we're going to talk about vectors. We continue the discussion. In this video, we will talk about how we denote vectors, how we write vectors, how we understand vectors. And then following out from that, we will start to discuss we're going into more detail with respect to certain properties of vectors, and then we look at how they relate to each other. All right? So there's a language in which you write about vectors. Like any other concept, there's a particular language. There's a language in which we speak about vectors, and there's a language in which we write about vectors. So we're going to delve a little bit into the written language of vectors, and of course tie it into how we speak about vectors. So anytime we have a vector, we assign two components to the vector. And I want to talk a little bit about the whole idea of a component before we start to write. Good? Remember, in your coordinate geometry, when you're locating a point on your coordinate axis, we talk about the x coordinate and the y coordinate. So in other words, there are two components of the location of a point on coordinate axes. Right? The components are expressed using the x and the y coordinates. If we think about geography, any place on the Earth's surface, we have north or south latitude, right? North or south of the equator, where the equator is reference point. Or we have east or west longitude, where the Greenwich meridian is the reference point. So again, any location on the surface of the Earth, any point can be located very specifically on the surface of the Earth by reference to the equator and the Greenwich meridian, which will give us two components of the location: east or west longitude, north or south latitude. And that is the same technology, the same concepts that you read about in books. That is the same technology that your satellites will use. That is the same technology that will allow you to use your Google Maps, for example, your Waze. All right? All these fancy technologies that we take for granted, they are taking basic concepts, the whole idea of location, the whole idea of a reference point, right? And they apply it in a slightly different context, and they bring right to you in the palm of your hand the convenience of being able to use maps. All right? Nice. So with respect to the mathematical side of it now, to be more specific, we use the coordinate geometry system when we're talking about vectors, generally speaking. And almost any vector quantity that you could think of can be expressed in terms of some variation of your coordinate system. Whether it's x and y, if it's a plane surface, a flat surface, or if we're talking about three-dimensional vectors, you have x, y, and z. Of course, I am sure we can denote dimensions with more than vectors, with more than 3 dimensions. I am sure that we can denote vectors with more than 3 dimensions, but that, of course, is outside the scope of our discussion here. All right? So let me start writing now. Yeah? So, generally speaking, when we have to denote a vector, the vector is denoted by a straight line with an arrowhead showing the direction. All right? You can have a straight line with the arrowhead in the opposite direction. So this brings me now to another property of vectors that I want to discuss. There's something that we refer to as the orientation. The orientation of a vector, and then there's the direction of a vector. All right? Now, those two concepts are closely intertwined. All right? If two vectors are, now listen to this, if two vectors are parallel, it means that they have the same orientation. Now, two parallel vectors could either be in the same direction or right? So they could be in the same direction. So if you have these two parallel vectors, let me say vectors parallel, right? They're in the same direction. They could be parallel, and they could also be in opposite directions and still parallel. All right? So we want to be very clear on the distinction between the orientation of a vector and the direction of a vector. The normal definition of parallel vectors is two vectors that have the same direction, which, to be very specific, will only apply if the two vectors doing this, meaning that the arrows pointing in the same direction. All right? But if you have a situation like this, parallel, right? If you have a situation like this, the two vectors, they're not pointing in the same direction. One going so and the other one going so, but they're still parallel. So that now is the difference between the orientation and the direction. So what I am trying to do here is to be very clear in terms of language, in terms of how we talk about this thing, which would mean sometimes I will introduce phrases that are a little different to what people are accustomed to. And that is fine. All you have to do is sit down and pay attention. All right? Now, if we go back to the coordinate geometry system, we remember we talk about the gradient of a straight line. All right? Now, if two vectors have the same orientation, it means that they have the same gradient. So we could use the word gradient here as an alternative to the word orientation, right? The gradient might be something that you're more familiar with. So in other words, this line has the same gradient as this line, but the direction described by the two vectors are opposite to each other. Same story here. Well, different story. In this case, they have the same gradient and the same direction. So you can have the same gradient and the same direction, or you can have the same gradient and opposite directions. Right? In both cases, the gradient are the same. So in other words, if we're talking about coordinate geometry, we talk about the gradient of a straight line. We don't normally use the word gradient when we're talking about vectors, but you could use it in your own thought process where you're talking about two vectors. Let us assume that the directions are opposed to each other. All right? But the gradient of the line that represents the line that the vector is on, the gradient of the line itself, the straight line, would be the same. All right? And if I could borrow some terminology from the circles, we can see that these two directions are diametrically opposed to each other. So in other words, if we're talking east and west, all right? We're talking east, using a cardinal point as a reference now, and you're talking west, right? So this is due east, this fella here is due east, and this fella here is due west. Now, for the purposes of geography, there is no way that we would say these two are moving in the same direction, right? These two are moving in opposite directions, diametrically opposed to each other, so to speak. However, the general orientation is horizontal, right? So you're getting a sense of what we're talking about now. The orientation is horizontal. You're moving east or you're moving west. By the same token, if we're talking north and south, right? This guy is going to the north, and this guy is going south. Again, for the purposes of directional description, there is no way we would say that these two vectors are traveling in the same direction. However, the orientation is the same, which is vertical. In this case, the gradient is 0. In this case, the gradient is infinity. All right? So we could talk about orientation in terms of general language, or we could talk about gradient in terms of specific language that is specific to coordinate geometry. All right? Of course, these two vectors are parallel to each other, and these two vectors are also parallel to each other. All right? So Actually, no, that's the wrong sign I'm using. That's the wrong sign, right? No. That's the sign for equal lengths. All right, let me forget that. Let me, and I'll tell you why I'm doing that now. You see the problem we have in here, right? And I will describe the problem in a little bit. That is the sign for equal lengths. All right? Now we know that generally in general usage, we say two lines are parallel, the arrows will be like this to show that the two lines are parallel. Right? But if we want to be more specific, we have to be very specific. The two lines are parallel not because they're moving in the same direction. So in other words, if we talk in general usage, if we talk in coordinate geometry, we could say, all right, they're moving in the same direction. But if we have to be very specific, which is where vectors enters the picture. Vectors, we're more specific than just saying, okay, they're pointing in the same direction. What does that mean if we say they're pointing in the same direction? Right? If we say they're pointing in a direction, well, here the next question. Which direction they're pointing in? And if the two lines not pointing in that same direction, then we cannot say that they're pointing in the same direction. So even though these two lines are parallel, unless the two arrowheads are moving in the same direction, they're not pointing in the same direction. Right? In this case, north and south, and in this case, east and west, they are pointing in the opposite directions. So you have to be very, very clear and specific when you're talking about the whole question of direction where vectors is concerned. All right? That would bring into question the whole issue of the negative sign, but we will deal with that later. All right? Direction is not the same as gradient. Direction is not the same as orientation. So two lines could have the same orientation, which means that they're parallel, but they could be traveling in opposite directions. Two vectors, sorry. Right? If we talk in lines, no problem. We could just use the language loosely and talk about direction. If we talk in vectors, we no longer have the luxury of being loose with our language. We no longer have the luxury of just talking flippantly about direction. If we talk in direction, we have to be very specific about which direction we're talking about. We're either going east or we're going west. It is no longer good enough to say, well, we're just traveling horizontally. Traveling horizontally means that you're in scalar mode. Scalar meaning we just know you're traveling horizontally. And even then, if we say you're traveling horizontally, you automatically impose a sense of direction now. So even if we just say horizontally, it doesn't really say anything. If we say horizontally, we're moving from scalar into vector. If we say just traveling, all right, no problem with traveling. If we say horizontally, now we start to talk about direction. But you ain't reach direction yet. You reach orientation. So the orientation of your movement is horizontal. But you haven't really said anything yet. You're either moving to the right or you're moving to the left. You're moving to the east or you're moving to the west, etc., etc. So in other words, it's different levels of being specific. Different levels of specific where we're talking about it. And part of my whole thing in teaching maths is to be very specific about the language that we use. Because part of the problem that people have in understanding mathematics is language. So for example, people might say, well, all right, two lines are parallel if they're traveling in the same direction. And then you start vectors now and you realize these two are traveling in opposite directions. And it's not occurring to you that the two lines parallel. Because your definition is that they have to be traveling in the same direction. So you come in a vector context now. And suddenly you have two lines where the directions are different. The directions are even opposed to each other. And yet, you have to describe the lines as being parallel. Because from a strict vector standpoint, being parallel is not about direction. Being parallel is about orientation. Right? So, sorry for rambling on a little bit, but sometimes I have to ramble on a little bit just to make a point. And sometimes this is the part of the discussion that where most people tune out. And then they'll come 2 months later and ask me the same question. That if they had just taken the time to listen when I was talking about it in the video, they would have gotten the little insight to make certain connections and understand the thing. So if you're still here, that's good. All right? Where we reach now? Right. So we talk about parallel vectors. Right? We could talk about the addition of vectors. We could talk about the multiplication of vectors. All right? Now, when we're talking about adding vectors, right? So we go in general here yet, right? We ain't start to go here yet. When we talk about adding vectors, remember vector is direction. Vector is direction. So it means that we add in one directional movement to another directional movement. So if we do this, if we do that, we move from here to here. And then we move from here to here. We go here and we go here, that's addition. Now, we add in if we travel in the same direction. Right? If we're traveling in the opposite direction, that is when we're subtracting. So, if we go from here to here, and then instead of going from here to here, we go from here to here. Sorry, hold on. That will force me to get a little more specific now, which I don't want to do right now. So let me go back. Let me take it. If I go from here to here, right? And I go from here to here. And then I go from here to here. Right? Then I here to here, and then we add from here to here, and then we add from here to here. So in other words, you move 3 times, and let me say that the length of the 3 vectors are the same. So in other words, you move the same distance 3 times. In the same direction. I mean, we add in. If, however, you come here now, and instead of going here, you come back here. Right? You move the same direction, the same distance, but in the opposite direction. You now minus and end back up here, where it was. Well, not where you started, but you end back up here. So we're going to use that now. We're going to come back across here and then go back across there. Well, no, we wouldn't come back across here. The first thing we have to talk about when we're talking about the language of writing vectors is how we write vectors. Right? Sorry, the first thing we're talking about when you're writing vectors is the usage of certain letters, lettering. So let us say that from here to here we call that A. And from here to here is another A. And from here to here is another A. So in other words, A plus A plus A, 1, 2, 3. And then you come back here. Now if A is defined as being this direction, whatever this direction is, then the opposite would be minus A. Alright? So if we go A plus A plus A, and then we come back here, we can say that's minus A. We'll come back to that just now. Now if you notice, A plus A plus A, let me stick to this here, is the same thing as 3A, which is we multiply a scalar quantity, which is a constant, by a vector quantity. Right? Remember the A is a vector. We'll get a little more specific as to what the A means in terms of specifying direction. But the A is a vector. All right? So in terms of movement, we could specify a situation where we could multiply a vector a certain number of times by a scalar. Now, if instead of this we have this, same direction, well, same orientation, but different direction. This is minus A. Let me go here again. This is minus A. And we go here again. Right? That's minus A. Right? So minus A. Let me say plus minus A. Plus minus A. Right? Because you go in minus, it will end up as minus A, minus A, minus A. Right? Right? Which is the same thing as minus 3A. So in other words, you now have minus 3A. Now what is the difference between 3A and minus 3A? As you could sense by just looking at the diagrams, the minus sign is what indicates the opposite direction. And that is the role of the minus sign where the vectors are concerned. Remember, the minus sign is a constant in mathematics, right? In most of the algebra, at some point you'll have to deal with a minus sign. But the minus sign means, means different things in different topics. All right? In some topics, the minus sign is about direction. In some topics, the minus sign is about division. Right? That is when you're dealing with indices and things. Different things. The minus sign means different things. All right? Etc., etc. In this case, the minus sign is a reversal of direction. Right? The minus sign generally denotes a reversal of something. Whatever you was doing before, if you put a minus sign, it means you're doing the opposite. So if you was adding the minus sign, it means you're subtracting. In indices, if you're multiplying, it means that you're dividing when you deal with the negative index, etc., etc. And there are a whole host of other topics. But the general idea is that the minus sign denotes some sense of reversal. We're reversing something. If we're talking vectors, right? Remembering that vectors is principally about direction. And we introduced a negative sign in vectors, it means that we're reversing the direction. That is essentially what we're doing. So A plus A plus A, that's 3A. And if we go minus A, 3A minus A is 2A. But look at the same 2A here. 1A plus 2A. So in other words, you could trace the movements representing A as transport in movement in one direction. And if you represent minus A as movement in the opposite direction, it means then that if you move from here to here, it means that there is minus A. So you're now talking about A plus A plus A, right? That is to go from here to here, and then you minus A to go back from here to here. So you'll end up with 3A minus A, which will give you 2A, or you could say A minus A would cancel out each other. This A plus this A is the same, 2A here. So from a point of view of direction, if we understand the minus sign as a reversal of direction, then even the simple addition of vectors makes sense. If we get us, and we're talking about starting from vectors that have the same orientation, right? So the vector A has the same orientation as the vector minus A, but they're traveling in different directions. And the negative sign is what differentiates between this and this. If we're talking north, south, east, west, right? We don't have a negative sign. So in other words, when we're doing geography, we don't have signs when we're dealing with geography. What we have are specific names for each direction. So if we go in so, we call that east. If we go in so, we don't call it minus east, we call it west. Right? That's geography, that is not maths now. If we go in so, we call that north. But so is not minus north, so is south. So in geography, we don't have the minus signs to denote the direction. In geography, we have a name for each of the reference directions. So we have the 4 cardinal points, and everything else is referenced to that. And again, the 4 cardinal points go right back down to your 2 reference orientations. Horizontal, which is east-west, vertical, which is north-south. In mathematics, however, all right, we have, instead of using specific names for each direction, as they would do in geography, in maths, we use the negative sign to denote a reversal of direction. So in mathematics, movement to the right, which would correspond to east in geography, movement to the right is positive, movement to the left is negative. In mathematics, movement up is positive and movement down is negative. So we bring the negative sign to denote a reversal. And that is why I see the negative sign, -5 going down, -5 going left, -1, 2, 3 going up to the left, -1, 2, 3 going down, etc., etc., etc. Right? So be very clear on the difference between how we denote a reversal of direction in geography versus how we denote a reversal of direction in mathematics. All right? So that's basically it. Now is where the thing gonna start to get nice. All right? And I feel I will stop here. I'm trying to break up the videos as much as I could. Right? I try not to go on and on and on whenever I have a video. So sometimes I will break it up, stop, and then start on a new video. Give you a chance to stop, get yourself, and come back again. There will be times when I won't have any choice but to go for 45 minutes straight. This, however, is not one of them. So I'm going to stop here now. All right? In this video, we would have spoken about, the main thing we would have spoken about would have been the whole issue of direction, how we denote direction, the whole issue of orientation versus direction, the whole issue of a reversal of direction being denoted by the negative sign, and of course, implicit in all of that is the discussion of multiplying a scalar by a vector. So in other words, if you move in the same direction 3 times and you define the vector A as being a particular direction, then the triple movement will just be 3A. And of course, if the same thing happens in the opposite direction, it will be 3A with a minus sign in front of it. The negative sign, of course, being used to denote the reversal of direction. All right? So stay tuned. We have plenty more coming. In the next video, we will talk about specific, even more specific aspects of how we denote direction when we're talking about vectors.